Recording is rolling. It is Monday, August 25th. So back on Thursday, Friday, you guys were gathering data for this car and incline labs. We're trying to figure out what equation or equations could govern the motion of a car, an incline, being pulled under some component of gravity. Okay? So by earlier class, we were able to get most of these graphs, and then time ran out. So we'll get as far as we can. Uh, no, you guys should also have an AP style write up. I did want to score those, but we probably won't have time to get to those today. You know, I also have to tell you guys, you guys are my green label class. You guys see those folders hanging from the lab tables back there with the green labels, right? The green label, your name is on one of those green labels. Okay, so I did get the trigonometry page back in there. So if you want to pick that up. Okay. So here's the plan for, well, next few days. So, okay, well, tomorrow we got to finish whatever we don't finish today, and including the lab write-ups. How do you guys score those? Right? And then I have a bunch of linear motion demos and posters and formulas to go through. This will take us a few days, so I'm going to get the ball rolling on this week really on linear motion. I've been promising you guys a quiz this week, so let's put that on Friday. Now, this quiz could be just anything that you guys have seen in class so far. So, I bet there's a good amount of trigonometry vector components on there. But there could be some measurement on there. There might be a little bit of linear motion, like the car and incline, because you guys have been doing this for a few days, including today. Okay. And then you guys know we're coming up to a 3-day weekend with Labor Day weekend, or Labor Day. And then next week, well, we'll probably have to keep going on linear motion because 2 days is not enough for that. Okay. And possibly get started on projectiles. So that's what we're looking at for about this week. Okay, so you guys last week had this car going down the incline. Okay, we're trying to figure out what are the relationships among all these variables. I split you guys up into these different groups. So if you have the clubs, you were saying, well, if I start taking lab masses onto this car, how does that affect the motion of the car? Okay. The spades, you're looking at distance versus time, and the diamonds and the hearts, we were saying, well, what could affect the final speed of the car, the final velocity? Okay, how much time, how much distance? Okay, with that. Okay, and we're about to put all these graphs together one by one. Are you guys ready to make all these graphs? Now you probably already have at least one of these finished. Okay, so we're gonna start with the clubs. You guys see math versus time up here? Clubs. Okay. Now, if you have the clubs, you probably already have this graph completed. Okay, if you don't have the clubs, then we're gonna make it real soon. Okay. Speaking of measuring mass, I have a bonus demo for you guys today. Okay, so this I just got over the weekend. You guys see this triple beam balance right here? Triple beam balance. Okay. Now you guys had a digital scale, but I really like this triple beam balance. So I want to show you guys how this works because a lot of students have never seen one of these before. I'll put this back in the lab table and just generally have it around because. So this works off a seesaw method. Actually, the principle is called torque, which we'll cover in this class probably in about January, but I'll tell you guys a little bit about it today. So if you get it, then awesome. And if not, then it'll be one more day to have this concept click. Okay. So I got this plate here and I got some sliders. It doesn't fit super well in the camera view, but I'll do as best I can here. So right now all the sliders are to the left and there's nothing on this plate. This thing is zeroed out like a seesaw. And if I hold it this way, which is down, this gravity's flowing, okay, then here I'll put my thumb on this and stop it, show you what it looks like. You guys see how this needle can swivel above and below the zero? Okay, so if I put a weight on the left side, it goes clunk, it goes up like that. Okay, and then what I can do is I can try to restore balance by moving these sliders around. So the one in the center is 100 grams at a time. So there's 100 grams, there's 200 grams. Okay, the one in the back goes 10 grams at a time, and this one gets a little stuck. So, okay, and this one in the front slides 1 gram at a time. You guys see it goes label 1 through 10. Okay, so let's see. So say I have this one. This came with the triple B balance. It's labeled 147.5 grams, which is pretty weird, right? I don't know if that shows up on camera. It says 147.5. Okay, so what I do, like right now, this is balanced. It's like a seesaw. You might be able to see that motion in the camera. See how it's just barely balanced there in the seesaw in the camera. Okay. So I put a 147.5 grams, so it's clunk. The whole thing tips that way, like to the left. Okay. Then I can slide these to restore balance. So maybe I slide over 100. Okay, it's still like this way. Okay. Maybe I go to 200. Ooh, you guys see a tip go, clunk and clunk the other way. Okay, so that's way too much. So I'll slide it back to 100. So it's 100 something. And it locks in place. You guys see these little notches right here. See these little ridges, these little notches. Okay. So I'll slide this one. Say it slide it to the 40. Okay, so it's still not enough. 140 is still not enough, but it's getting kind of close. If I go 150, that's too much. It goes clunk and it falls down that way. So I got 140 something. And then that's what I bring up the 1 gram guide for. If I slide it to about 147, okay, it needs a little more, and then 0.5. And once I do 147.5 right there, yeah.
For our lab right up, you said don't use speed gate or can for quick.
Yeah, you can use that. Yeah. Okay, just on the actual AP exam, they don't know what that particular tool is.
All right.
Just call it a motion detector, but you guys can use speed gate. Yeah. Okay. So now at 147.5, see if I stop this with my thumb right here and show you guys. Okay, it's just hovering at the 0. It's just hovering at the 0, right, where it's not above or below. Okay, so then I know that this measures 147.5 grams. Is what it would be. Okay, so I'll have that. Now, I'm gonna do an extension activity with this. Okay, so again, if this clicks makes sense, awesome. And if not, then we'll be covering this more in detail on probably about January. Okay, you can actually, if you have one known mass, you can find the mass of any unknown value using this method. So here's a seesaw. I'm going to set up my seesaw on this pivot right here. Guess this pivot? Okay. Which here, I'll set it up right in front of you guys right here. Here's my pivot right here. Here's my ruler, here's my seesaw. Actually, let me turn this so you guys can read the centimeters. Is that? Okay. You guys see this ruler right now is balanced pretty much right on the 15 centimeter mark. So, right around the 15. You guys see that? It's balanced like a seesaw. Okay. Now, suppose I have two masses, one known, one unknown. How about these guys? Okay. Let's say, now, of course, you know what they are because the number's stamped in it. You guys saw that last week too. This one says 50 grams. Let's say I'm allowed to know that. I know that this one's 50 grams. And this one, well, it says 20 grams, but let's make believe that we don't actually know what it is. Okay, so I have some mystery weight. You guys have some mystery weight. Okay. Now, I should be able to put these on here and slide them around until it balances somehow. So let's see where that would be. All right, well, we'll do some actual science right here. So, and I've used this method just in the wild many times. Many times this has been a helpful thing to know. Okay, so think of it. Okay, now I need to balance it at 15. So I need to slide this way. Okay, maybe a little more. Here, no, too far, but it's right close to there. It's like right in there somewhere. That's really, really close. Okay, so I'm going to stop this right here because that's where it was like balanced. Okay, so the 50 grams is on about 19.7, about 19.8. Okay. And the 20 grams is like on the 2.7. So do that. Oh, I'm going to just draw exactly what happened. So at the 50 centimeter mark is the pivot point. Or sorry, not 50 centimeter. That would be per meter stick. Sorry, the 15 centimeter for this little ruler. Okay. This 50 gram is balanced out. So it's 50 grams. Okay. And this is like at the 19.8 centimeter mark. Okay. And I have some unknown lab mass. I'll call it M for mass when I saw it. And that's at the about 2.7 centimeters. Okay. I don't know if these are exact, but I haven't tried this out ahead of time. So the numbers aren't pre-tried or anything. So I just did that real time. Okay. We're going to see if this method works. Okay. So can I solve for this Mr. Mass, which ideally should be 20 grams, right? Okay, guess what I said? Okay, so this goes through a principle again called torque. I'm gonna write that down. TORQUE, torque. Okay. Kind of like turning a wrench, opening a door. Yeah, do this with you guys. You guys ever open a door? Now, why is the handle right here opposite of the hinges over here? Why not put the handle right next to the hinges? Would it be really, really hard to open the door? Yeah. Ooh, really hard. Versus if it's over here, ooh, it's really easy to open the door. Right? That's what this is right here. And the formula goes like this. So it's Greek letter tau. Yeah. It goes R cross F. That crosses a special kind of multiplication called cross product, some kind of perpendicular type motion. Okay. So F is the force you apply, maybe in Newton's like push. And R, that's like the radial arm. Okay, that's why you want the handle to be opposite of the hinges, because it maximizes that radial distance, doesn't it? And with a little tiny force, with a huge distance between the handle and hinges, you get plenty of torque, opens the door, releases. Okay. How about you use a wrench? Guys, use a wrench. Do you want a really long handle on the wrench? Yeah, same reason. Okay. So what about here? Now, I'll do a little lecture with you guys, give you guys a bigger picture of what's going on. Here's my seesaw, which is like my ruler. My seesaw is my ruler, right? To get how many forces basically are acting on us?
Really just grab.
Yeah, these two pulling down. Yeah, and a third one for. Don't forget the pivot's also pushing up. I guess maybe a fourth one if you threw in its weight, but that'd be really tiny. So basically three that matter. Like these two pulling down, and also the pivot's pushing up. What do you guys think? What if I do this? The sum of the forces is equal to. Guess what the sum of forces would be if it's all balanced? Zero. Yeah, 0 newtons. So the two down and the one up balance out. Okay. Guess what the sum of the torque has to be if it's all balanced? Also zero. Now the units would be Newton meters because force would be newtons and radius would be meters. Okay. Right. And we're going to take advantage of that. So I'll say relative to this pivot point. You guys see put a big old X there for this pivot point? Okay. So at this radial arm to the left, I've got some downward force, which is causing or trying to cause a counterclockwise torque. So this could be a force, this could be a torque. Okay. Then, again, relative to this pivot point, going to the right, I have some different lever arm. Actually, it's not as big. Call this R1, call this R2, F1, torque 1. Okay. And then there's a much bigger force. Ooh, call it F2. That's trying to cause a torque that's clockwise. I'll call this torque 2. But you guys know torque 1 and torque 2 should just zero out. Okay, oh, well, one's counterclockwise and one's clockwise, so they sort of subtract from each other. Is that true? Right, so let's put this together. Let's say torque 1 minus torque 2 equals 0, or the left torque equals the right torque in terms of magnitude, okay? Which is R1 F1 equals R2 F2, right? So that's a radial arm crossed with the cross product. Okay. Now the force is actually, do you guys remember the difference between mass and weight? You guys remember if I do this with it? Guys, right now I'm getting a sense of what? Mass or weight? Mass. Yeah, mass or inertia, right? Which would be the same on the moon, wouldn't it? But if I pick it up, pick it up, now I'm lifting it against its weight. That's a force. Okay. So what weight turns out to be with force is mass times gravity field. Here, I'll spell it out today. Grav for gravity field. Okay. And over here, I've got a different radius and a different mass, say m2, times also Earth gravity field. Okay. Because Earth gravity field and Earth gravity field, wouldn't these be in the same Earth gravity field? Is that true? Okay. So since that's true, I'm going to start popping numbers in. So this R1 right here, who could tell me, maybe I'll pull up this with you guys, who could tell me what is this radial arm from here to here? Yeah, 12.3. Yeah. Right. So in place of R1, hit 12.3 centimeters. Okay. For M1, well, let's just our mystery M mass, which you guys know should be 20 grams, but we're going to find out. Is that true? So I'll treat this as a mystery mass right here. Okay. And then R2, guys, what's this distance from here to here? Huh? Yeah, 4.8 to 4.8 centimeters. Okay. And then, no, I'm allowed to know this one. Got to know this one. So I'll call this guy 50 grams. 50 grams is the mass. Okay, the Earth's gravity again. Canceled out. Okay. So can you solve this in one math set at this point?
Yeah.
Just divide down to 12.3. Is that right? Okay. We're about to figure out what is the mystery mass. So let's see. So I'll take 4.8 centimeters times the known 50 grams. Okay. And then divide down this other radial arm, which is 12.3 centimeters. I'm getting, oh, look at that. Look at that. 19.512, call it 19.5 grams. Yeah, that's really, really close, isn't it? Like, the actual value was 20 grams, so yeah, I'm happy with that. Okay, you guys how that worked? What's that? Okay. And I'm showing you all this for a couple of reasons, well, a few reasons. One is that this is just handy to know in real life. I've used this. You're going to run into this in a few months anyway, so better plant that idea now, and then that much easier to learn in the future. And that is exactly the principle that this works by. Okay. Oh, I forget if I asked you guys, but I'll ask you guys anyway. Okay. What if, guys, remember how this measured out to 147.5 grams right here, and that zeroed this out and it leveled out? What if I took this tool right here, with this lab mass to the moon? Would it still read 147.5 grams on the moon? How many guys say yes? How many guys say yes? Yeah, you're right. If you raise your hand, you are a winner. And what part of this process tells you that this would also work on the moon?
The gravity.
Exactly. The gravity field cancels out. Yeah. Now you need at least a little bit of gravity to make it work. But once you have some, it turns out it doesn't matter what the magnitude is. Cancels out. Yeah. All right. Okay, so there's a different way to measure mass. So yeah, speaking of measure mass, let's get mass as a function of time. So we're all about to make that club graph, that graph in the top left of your page. Okay. So I'm doing mass versus rolling time. Who are the clubs? Was that okay? You guys, right? Who feels really good about their data and wants to share their data? All right. Let's see. Yeah. How about Adeline? How about Adeline? All right. So I'm setting this up now. Did you measure mass in grams or kilograms?
Grams.
Grams. Okay. So I'll do the same thing. So we put m as a variable, and then as a unit, I'll put grams. Okay. And I'll put t as a variable, time, and that'll be in seconds. Okay. Now, one question I got last week was, well, aren't there rules about which variable goes on which axis? Because generally speaking, what goes on the horizontal axis? Your independent or your dependent variable? Independent. Like that's a rule, right? Should independent go down here and then your dependent should go on the vertical generally? Okay. But there's another rule that overrides that rule, which is if time is ever ticking along, then as a rule, you always put time down this bottom axis. Okay. We're going to do tons of graphs in this class, so the more we do, the more it'll make sense why that's actually a good convention. Okay. So, Adeline, what's your you know what? Before we start making this graph, I need to run a hypothesis with you guys. So if you were in one of those graphs with, if you're one of those groups with the clubs, then you should know what the answer is already. But how about everybody else? Everybody else, I want you guys to hypothesize. If I'm adding more and more lab weight to this car, just throw on some tape here, make it heavier, heavier, heavier. That's going to do one of three things. One thing you could do is it could make the car zip down the incline faster. That's to say, if I increase the mass, that would decrease the time. Wouldn't that be some version of an inverse type relationship? Okay. Another possibility is maybe I take on more lab mass and it slows down the car because it has more and more inertia. Ooh, wouldn't that be some version of this? I don't know if it'd be straight line, but more mass and more time it would take. Okay. A third possibility is that maybe I take on more lab weight and it makes no difference at all. Right? Maybe a light car and a heavy car would tie, and that would look something like this, wouldn't it? For lots of different masses at the same time over and over and over. Okay. Now let's see. Show of hands. What do you guys think? How many of you guys think as I increase the mass of the car, it's going to zip down really fast and decrease the time? Who says that? Okay. I got some votes on that. Who thinks as I take on more lab mass, it's going to slow down the car and make a graph that looks some version of that? Who thinks that one? Okay, that's got some votes too. Okay. And who thinks that there's no relationship? That's to say that I have lots of different mass cars, but they all pretty much at the same time. Who thinks that one? No? Okay. All right. Ooh. All right. All right. We're gonna see. We're gonna find out. So it looks like all those three hypotheses have votes to them. So everybody thinks one of those possibilities. Let's figure out what it actually is. Okay, so Adeline, what was your heaviest car?
Heaviest car was 128.6 grams.
128 point something. All right. So we got to scale this. Let's scale up to how about 150? So kind of go 25, 50, 75, 100, 125, 150. Yeah. Oh, guys, are your graphs always going to start at 0, 0? Yeah? Yeah? Okay. Especially for this class. I can't think of any exceptions. So I think in this class, the graphs are always going to start at 0, 0. Okay. So I'm doing 25 grams, 50 grams. Well, the unit is already embedded in the axis grams. So you got 75, 100, 125, 150 is up here. Okay, you could subdivide that into 5 grams at a time. Okay, and Adeline, what was your longest time to roll down?
2.58.
2.5 something seconds. Let's go 1, 2, 3. So 0, 1, 2, 3 seconds. All right, so everything will fit in there, right? Fit in there? All right. So I need some coordinates. So what's one coordinate?
First one would be 2.58. 2.8.6.
And what was the mass?
28.6.
28.6? Okay. So 28.6. Okay. So you said 2.58 seconds it took for 28.6 grams to roll down. Okay. So there you go. Got a point on the board. All right. What's another coordinate?
2.36 with 38.6 38.6 grams.
38.6. 2.36 and 38.6. Okay, that'd be seconds and grams. All right. What's the third point?
2.46 seconds, 48.6 grams.
48. 2.48, 48.6. Okay, seconds, grams. All right. What's the fourth point?
2.43 seconds, 78.7.
So 78.7.
Mm-hmm.
Right about here. Sorry, 2 point what again?
43.
2.43 and 78. So okay. Seconds, grams. Okay. And
Okay, the first point on the left side. You said that?
okay. And you had one more?
2.52 seconds with 128.6 grams.
128. 2.52, 128 seconds, grams. All right, yeah, that's about what that graph looks like. So, can you guys draw a line of best fit? Because you guys know with these labs, especially with the stopwatch, yeah, there's always going to be a little plus or minus. They won't lie exactly on some curve or some line, but give or take a little. Okay. But you guys see like the overall trend. What should you draw? Here, I'll ask you guys. Which category, which basic category do you think this falls into? No relationship. Yeah. Now my example is showing a horizontal line, but isn't a vertical line also an example of no relationship? Zip. Just like that, right? Just like that. Okay. Because look, it turns out it doesn't matter if you have light cars or heavy cars. That particular incline, it took them all about 2.5 seconds to roll down. Yeah, regardless. Okay. All right. Oh, and of course, you guys have a constant angle and a constant length. I just meant to emphasize that too. Right. Here, just for completion, what angle did you guys use? And what length did you guys use? 5 degrees. And the length was how long? Was it 200 something centimeters? Maybe 200 centimeters, something like that. Probably something like that, right? All right, there you go. All right, and of course those were controls though, so those variables were not changed. Right. Yeah. How about this? I forget if I mentioned the story, but I'll probably mention it a lot this year. Back in 1589, there was Galileo. He ran to the top of the Leaning Tower, and he had something heavy and he had something light. There's Galileo back in 1589, Leaning Tower pizza, and he dropped both of these. Which one hit the ground first? Same time, right? Now, wait a minute. Isn't this big one? Isn't it heavier? Doesn't it have more gravity force? All right. So, all right. So that should make it win the race to the ground, except that it also has more what? Inertia. I'm looking for. Yeah, inertia. Right. Now, eventually in this class, we'll get to something called Newton's second law of motion. And it turns out that those two properties sort of cancel out. So yeah, it doesn't matter if you have small stuff or big stuff. And I'm ignoring air drag, right? That's a complicating factor. But in this class, we tend to ignore air drag. Okay? So yeah, they would all hit at the same time. Yeah. Well, guys, your guys' car and incline lab is just a slowed down version of that same experiment. Yeah, it's just a slowed down version. But it's otherwise the principles are all the same. Right? There's some component of gravity that's pulling these Hot Wheels cars down the incline. Some gravity field going. Right. So got one down.
Mr. Griffin,
Oh yeah.
does that mean like if you're gonna go down a water slide, if we're like me versus like a 7-year-old, we would still end at the same time?
Yeah, as long as
you're the same size.
Yeah, they pretty much, yeah. So if you have little kid going down slide and like a big guy going down slide, yeah, they should pretty much tie. Yeah.
As long as you're the same size. Or shape.
And you'd be pretty close, yeah. Be pretty close. Yeah. All right, you guys ready to move on to spades here? Spades? Who had the spades? All right, so you guys all had spades? All right, so we're figuring out what's the relationship between distance and time. Right, so who feels pretty good about their data, wants to share their data? All right, so let's go, Gabriel. All right, so same thing is I'm gonna get a set of axes going. Oh, no, we're actually going to make 2 graphs for these, but we'll start with the one that says x versus t. All right, this first time. So, Gabriel, did you guys measure in centimeters or meters?
Centimeters.
Centimeters? Okay, so I'll do the same thing here. But distance in centimeters as a function of time the car could be rolling in seconds. Right? Oh, what was your longest distance?
The longest distance was 220.
220. Okay, so then I can use that to scale this. I can go 50, 100, 150, 200, 250. So go 0, 50, 100, 150, 200, 250. And what was the longest time it took for the car to go down?
The longest time was 3.25 seconds.
3.25.
3.01.
What? Sorry, what?
3.01.
3.01? Okay. Let's go 1, 2, 3, and then 3.01 is just a shade more than that. So that'll fit. Right? So 0, 1, 2, 3 seconds. Okay. Okay. Now, does everybody kind of agree that the more time you allow the car to roll, the further it's going to roll? That makes sense. Okay. Now, what I want to figure out more specifically is exactly what is that relationship? Here, I'll throw 3 ideas at you guys. It might be a direct relationship. And what that would mean is if you let the car roll for double the time, it would roll like double the distance. Okay. Or it might be maybe something that bends like this. So maybe the distance is increasing but at a slower rate. Or it might be something kind of like this, where if you let it roll for double the distance, maybe it's like, double the time, maybe it's like 4 times the distance. Ooh, maybe something like that. Right? So, I wonder which one of those is going to be. Okay. Let's get some points on the board and figure this out. All right, so Gabriel, what was one of your points?
For 220 centimeters, it was 3.01 seconds.
220, 3.01. So 220, 3.01. So at 3.01 seconds, 220 centimeters. Okay. All right, what's another point?
For 180 centimeters, it was 2.73.
2.73. Okay. So 2.73 seconds for 180 centimeters. All right, next point.
140 centimeters, 2.52 seconds.
2.52 to go 140, so?
Yeah.
Okay, seconds, centimeters. All right, next coordinate.
For 100 centimeters, it was 2.14 seconds.
2.14. So 2.14, 100 seconds, centimeters. All right, and
For 60 centimeters, it was 1.67 seconds.
1.67. Right there. Okay, 1.67 seconds to go 60 centimeters. Okay.
We can assume that it's 0 seconds if it went nowhere.
Yeah, that's a good thing to think about too. Yeah, because would 0, 0 logically have to make sense, right? So at 0 seconds, it's moved 0 centimeters. So this is kind of a point too, isn't it? Okay. All right. Okay, makes sense. Now, with all that, that was all your data. Okay. With all that in mind, where's here you go. Okay. Which category do you think that falls into? Parabola? Are you guys all saying parabola? Okay. Is anybody Sailor here? Sailor here? No. Okay. Because earlier there were some students who thought it was linear and they had a pretty similar looking graph. Okay. And sometimes it's kind of hard to tell apart linear versus parabola versus linear versus root. Okay, right? Because at a glance you would say, "Oh, aren't all these points lined up in a straight line? I could just hold my ruler right there and zip and do the line that's straight. Looks like a straight line. It almost looks like a straight line." Okay. Right. But yeah, what Guy says is maybe illuminating too. Because guys, if this was a straight line, what you'd be saying is that after a few seconds, it hasn't moved anywhere. In fact, as soon as you let it go, it looks like the car immediately jumps backwards. Right, so you let it go and it like jumps back 100 centimeters, which doesn't really make any sense, right? Okay, so yeah, the fact that 0, 0 should be a point. And if you aren't sure, could you, if you had to, could you go back in the lab and say let the car roll for like a half a second and 1 second and get some points right here? So you can figure out for sure, like more scientifically, right? Empirically. Okay. But yeah, you guys are right. You guys said it has to look something kind of like that, which might be more like a parabola, or I think it's a parabola. I think. Right? But how do you know if it for sure it's a parabola and maybe not some other shape that also kind of bends up like this? Okay, and that's what the next part of this is for. Right, so some kind of curve of best fit. Now I'd really like to know. So x distance rolled is some function of the time it's been rolling for, t. I suspect it's some kind of t-squared relationship. I want to confirm that for sure, but I also want to know exactly what is this equation. I can figure out exactly what this equation is. Okay, and for that, we're gonna move on to the next graph. Okay, guess the next graph. Okay, so we just did x versus t. Everybody has x versus t, right? We just did that one. It looks like it's probably a parabola. The one right by that says x versus t squared. You guys see that? Okay. I think I had you guys in class. Now, especially if you had the spades, I wanted you to do this. Create a column that says time squared in square seconds. Okay. Now, because this is a really abstract idea. Because what is square seconds? I don't know if it's really anything. Okay. But it's going to do something really nice in terms of a graph that let us whip off an equation really fast. Also, what we're about to do, like what we're doing right here, x versus t squared, this is a process that AP is going to want you to know. This is called linearization. So we're doing distance versus time squared. So this should linearize. Let's see if it does. So we're going to say distance squared and centimeters being squared. Okay. As a oh no, I'm so sorry, I messed up. Okay. So we're keeping distance in centimeters. Distance in centimeters. Oops. Okay. The time ratio. So time squared and square seconds. Okay. So the vertical axis is going to be the exact same as before. We're going to just let's go up to, well, I can just kind of trace it. 50, 100, 150, 200, 250. So 0, 50, 100 centimeters, 150 centimeters, 200 centimeters, 250 centimeters. Okay. Those are all centimeters. Okay. But the times, see if the biggest time was a shade over 3. Guys, what's 3 squared? 9. So maybe I should scale this up to at least 9. Right? Let's go about 2, 4, 6, 8, 10. So 0, 2, 4, 6, 8, 10. I'll throw my odd numbers right in the middle. Point, point, point. Okay. Okay. Do you guys have all the times squared already? Okay. Yeah. So you guys can tell me the coordinates. All right. So what's one coordinate on this page here?
220 and 9.06 seconds squared.
220, 9.06, 9 point. Okay. So 9.06 and 220. That's of course square seconds and centimeters. Okay. All right. Next one.
180 and 7.56.
180 and 7.56. Okay, 7.56, 180. That's square seconds centimeters. All right, next one.
140 and 6.35.
140, 6.35. 6.35, 140. Okay, square seconds centimeters. Okay, next one.
104.58.
104.58. 0.58, 100 square second centimeter. All right, and
60 and 2.79.
60, 2.79. The 2.79 and 60. Of course, that's square seconds and centimeters, right?
And
then-
of course, we assume 0, 0.
And 0, 0. Ah, right. Because 0 squared is still 0. Like this would still logically be a point 2, wouldn't it? Ah, yeah. Right. Now, look at all those points. What relationship is that going to fall into? Which one? Oh, yeah, I think it's linear right here. Or like a direct relationship. That would be a direct relationship, wouldn't it? Would be linear. You just take your ruler. You just do a line of best fit right here. Goes zip. Yeah, yeah. That should be it. Okay. Guys, it's easy to get the equation of a straight line. You just do rise over run and get the slope, and then do like y equals mx basically. That's it. Okay. Versus before, like if trying to figure out like what is the equation of that parabola? Like, I mean, I guess I could sit here all day and kind of figure it out, sort of, right? But if you linearized it, you just line of best fit, slope, zoom, boom, done. You got it. Okay. All right. So it's the same equation, guys. Is the equation for this and the equation for this going to be the exact same equation? Yeah, it's just on different axes. That's why the shapes look different. It's on different axes, but it's the same equation. Relationship between distance and time. So let's figure this out. What is the slope of this line here? Now, guys, here's like the proper way to do this is to choose the line of best fit that you made. And there's a statistical regression, like exactly to make it, but you could just throw down your ruler and pick 2 points on the line and find the slope between those 2 points. Okay? Okay. AP is going to want you to do that. If you have to write it out, describe what you did. Say you picked 2 points on the line and did a algebra run, find the slope. Okay. Now what I'm going to do, just to save us a little minute here, is I like this origin point, and I like this point because pretty much almost exactly through the line. Okay. So I'm going to do rise over run between this point and this point, and that'll give me the slope on it from here to here. Give me the slope. Yeah. Okay. So I'll say slope is, well, rise over run if you like. Okay. That's going to be like it's like 220 minus 0. So 220 centimeters minus 0 centimeters over, and then run could be 9.06 square seconds minus 0 square seconds. Is that true? That would be the slope. Okay. Okay. And then see what is that? What's 220 over 9.06? Okay. So that comes out to 24.28. I'll call it 24.3. That would be, guys, what would the units be for this slope? What's the units?
I mean, it's
Yeah, centimeters per second squared. Because centimeters on the top and second squared is on the bottom. So it's called centimeters per second squared. Okay. Now that's the slope. So to make an exact equation, so you can predict how far is the car going to roll after rolling for some time, I can say X, how far the car is going to roll. Now I can make a prediction. Now I can tell you. I can prophesize the future. I know exactly how the car is going to roll because I know physics. How can you finish out this equation right here? X equals what? Isn't it just slope times the x-axis or the horizontal axis, which is t squared? So it'd be 24.3 centimeters per second squared times time is my independent variable squared, or well, the variable, right? Horizontal axis variable. That right there is the equation of that line, right? It's the equation of the straight line. But if I graph this x versus t, wouldn't that exactly give me this parabola? Okay. Which is also the exact same equation. Guys, these two are the exact same equation. Isn't x equals t squared like a parabola? Like I said. Okay. All right, guys, good? Okay. How about this? Let's do some predicting. What if the car had only rolled for 1 second? If it only rolled for 1 second, how far would it have rolled? Yeah, about 24.3 centimeters. Because 1 second, you square that, multiply by this. The seconds squared, cancel, gives you 24 centimeters. Okay. What if the car rolled for? Okay, go.
I have a question.
Okay.
Because the relationship is parabolic.
Yeah.
Surely isn't that the relationship between the distance and time becomes almost negligible?
Well, it's a square relationship. So, I could plug in any time. Here, let me sort of try to use it this way. Okay. Because let's do a proportional. Let's do a proportional relationship. Okay. What if you let the car roll for some time? I don't know, 1 second or any time, and then you went back and you doubled the amount of time that the car rolls for. Okay. Now, just the fact that it's a parabola has nothing to do with this exact 24.3 centimeters per second squared. Okay. Just the fact that x is proportional to t squared. If you let the car roll for double the time, it's going to roll how many times as far?
4 times.
4 times. 4 times. Guys, if you throw a factor of 2 on this t, what's 2 squared? 4. Okay. What if you let the car roll for 3 times the amount of time? How far would it roll? 9 times as far. Because a factor of 3 squared would be 9. Here. And if you're not sure, you can try this out. Let it roll for 1 second. Well, 1 second is to roll 24 centimeters. Isn't that true? Okay. What if you let it roll for 3 seconds? Let's do 24.3 times 3 seconds being squared. Okay. Now, if I compare that back to the original, I'll divide that. So divide by 24.3. I bet this is going to tell me 9. This should tell me exactly 100. So I plugged in 3, then I plugged in 1, and dividing 2 should tell me exactly 9. And it is. It's exactly a 9 times ratio for the distance. So 3 times the time is 9 times the rolling distance. Okay. Right? Like I said. And that should carry on. So if you let it roll for 100 seconds, and then you double that up to 200 seconds, it's still going to be 4 times the rolling distance. Okay. All right. What's about this one? Oh, yeah. You know what? Okay. So I'm trying to have you guys discover these bit by bit, but let me show you guys where this is all leading. Okay. There's eventually these 3 kinematic equations that or formulas that can sort of govern all linear motion. Okay. And the one you guys uncovered right now is basically a version of this top one. Did you guys give a car a push, or did you just let it go?
Let it go.
Let it go. What do you think this V naught stands for right here? Initial velocity. Initial velocity. And if that's 0, doesn't this term just go away?
Yeah.
Okay. And what this will tell you is how far something falls or rolls as a function of time in an accelerating environment. And isn't the car going down the incline in accelerating environment? Because it's some component of gravity, which I'm about to bring up too. Okay. I want to try this right here. Guys, what was your incline angle?
We have no idea. We didn't measure it.
Oh, they measure. Did you use the one with the printer box set up, or did you use one with the textbooks? Textbooks. Okay, I'm gonna guess it because those were approximately 6 degrees. I'm gonna guess that was 6 degrees because these are normally about 6 degrees. Okay, with that in mind, we go a few weeks ahead in this class to oh, I thought I had this ready. I had this out. Hang on a minute. Where did I? Hang tight. I'm gonna see if I can find this real fast. Okay. All right. We're back here. Okay. I lost one of the posters, but guys, if you're in class, you guys see the one over the wall that says 0 friction incline? Okay. Now there's a whole actually it's not even that complicated, but there's a procedure that leads to this. But it says basically for your scenario of like a 0 friction incline, the acceleration ends up being Earth's gravity field times sine of this angle right here. Okay. So I want to see how close. Yeah, I have a poster for it. I'm sure it'll show up at some point. I want to see how close you guys got it. So, does anybody happen to know what is Earth's gravity?
9.8 meters per second squared.
Yeah, 9.8 meters per second squared. Okay. So, in terms of centimeters, could that be 980 centimeters per second squared? Yeah, 9.8 meters per second squared is what we're going to use. Okay. A lot of times I'll round that to about 10 meters per second squared. Okay. And yeah, this will be physics from a few weeks from now, but just to cut to the chase here. Say sine of, and I'll pop in a 6-degree angle because you guys had a 6-degree angle. Okay, this should be equal to this 1/2 a bit right here, shouldn't it be? Okay, because it's like, here, let's see what this is. Okay, how much is it actually accelerating? 980 sine 6 degrees. So I'm getting 102.4. That'd be centimeters per second squared. Okay, now, okay, so you're close enough. Right. So now keep in mind, your guys' cars, you guys think there was realistically maybe a little bit of friction. It was like rubbing against the sides of the incline a little bit. So this should be like an upper boundary. And maybe your car had a consistent acceleration, but it was a little slower than that. It's all right. Okay. But this right here takes the place of this 1/2 a. Okay, remember this bit 0. So x is 1/2 at squared. Okay, so this x equals, wouldn't 24.3 be 1/2 of a? Okay. So let's try this. If you do 1/2 of the acceleration should be 24.3 centimeters per second squared. Then shouldn't the acceleration be 48.6 centimeters per second squared? Something like that. That'd be true. Okay. Good. In fact, yeah. Okay. So something up there. Right. And if the upper boundary is like 100 centimeters per second squared, yeah, that's kind of the ballpark. Pretty good. Pretty good. All right. Let's see how we're doing on. Okay. Let's do. Next one is speed versus time. Okay, so diamonds. Let's do diamonds. Who had diamonds? Right, you guys. Okay. So, all right. Lily, what was your B versus P? What was your fastest speed?
2.67 seconds.
Okay, so 2 point.
Oh, sorry. It's 168.94.
168. Okay, let's scale this up to 200. 50, 100, 150, 200. This would be centimeters per second. 0, 50, 100, 150, 200. And your time with longest time was what?
2.68.
2.68. Let's go 1, 2, 3. So 0, 1, 2, 3. All right. So let's go. So what was one of your coordinates? One of your coordinates.
0.96 and then 65.34.
65. That's right there. 0.96. You said 60.
5.34.
Okay. So seconds. Centimeters. All right. What's another one?
1.68.
1.66,
and then 103.0.
103.0, 1.68, 103. Okay, next one.
1.98,
1.98,
and then 130.34.
130.34. But no, 130 is what I got here. Okay. 1.98, 130. Okay, next one.
And then 2.3,
2.3. And
and then 151.07.
151. So 2.3, 151. Okay, and the last
And
one.
then 2.68,
2.68,
and then 168.74.
168.
0.94.
What? Sorry, say it again. 2.68,
2.68, and then 168.94.
168.94. Okay. All right. Okay. Now, guys, what relationship do you think that is? Zip, right there. What is that? Is that linear or direct? Yeah, that would definitely be this one right here, wouldn't it? Okay. And what we're sort of getting to is, you guys see this formula right here? So if you did not get the car push, it starts from rest. Isn't it basically this speed? Oh, do you guys think VF is final velocity? The speed the car is zipping through that speed gate right at the bottom is acceleration times time. Okay, let's see if I can get the acceleration off this. What's the acceleration? So okay, we'll take this point in the origin. So it's 168.9 divided by 2.68. That'd be, hey, look at that, 63 centimeters per second squared. That's kind of in the ballpark of what everybody's gonna get. All right, so right there, yeah, that's pretty good. You guys good so far? All right, so tomorrow we'll have to do the hearts and then have you guys grade your AP write-ups. But yeah, Bill's about to ring, so that'll be a close on class today.